ready for this one, we need to find and classify our critical points. So what are critical points? Where the derivative is 0 or
undefined.
undefined. Okay, have to check for both. So find our derivative. Oh, I forgot to hand back your quizzes. It is derivative. I'll hand back. So derivative of 4 is 0. X to the 1/3 would be 1/3 x to the negative 2/3. Alright, so then if you wanted to rewrite that, that might help you a little bit. A negative exponent, puts it on the bottom. So our critical point is anywhere this equals 0 or undefined. If I just set this equal to 0, first thing you do is multiply over your denominator. 0 times anything is still 0, and you get 1 equals 0. So does that happen? No. So there's no critical point where the derivative equals 0. The other possibility is undefined. That's one fresh here. We're not going to get another form tape for a while. So where is this undefined?
It would be at 0.
Mm-hmm.
Because it's cubed root, you don't want to.
Right. Well, so this is a place where it's undefined. So that is a critical point. It is our only one. So when we test, we need to look on each side. Because it's a cubed root, we are able to put in negatives for this. So let's put in, we're going to do a -1 and a +1. When you plug these in, do you put them in the original or the derivative? Derivative. If I put in a -1, -1 squared is 1, cube root of 1 is 1, 1/3, so that's positive. If I put in a 1, still 1/3. So it's positive on both sides. What does that tell us? Yeah, it's something, we still had potentially a horizontal tangent line there, but there's no change, so it could be like something that's always increasing, or it could be like the cube root. Either way, that means there is no local maximum. Alright, so we know what the first derivative does, but we know you can do second derivatives, or third derivatives. So let's talk about what a second derivative tells us. I didn't put this one on your handout, did I? So think about a graph. Okay, if I'm looking at this function, the derivatives of both of these would be positive, would they not? If you drew your tangent lines, these all would have positive slope. These would all have a positive slope. What's the difference? That's what they're drawing. The curvature. This one's kind of curving upward. This one's kind of curving downward. If you think about your derivatives, let's think about second derivative for a minute. This first derivative is the slope of the tangent line. Second derivative tells us the slope of the first derivative, right? These tangent lines are getting steeper as we go on, so when you do that second derivative, it will still turn out to be positive, because these slopes of the tangent lines are increasing as time goes on. This one, these are all positive, but what's happening to these lines? The slope is decreasing. What's going to happen here is your second derivative will turn out to be negative. Second derivative tells us what's called concavity. This is a graph that is concave up. It's curving upward, or think it could hold water. If you want to hold water in your hands, you're going to curve them upward like this. This graph is concave down. It's curving downward. In general, if the second derivative is positive and it's concave up. If the second derivative is negative, it's concave down. So the way I worded it on yours, I didn't really use this definition. If f double prime of x is greater than 0, the graph is concave up. If your second derivative is less than 0, the graph is concave down. So let's look at this a bit. We've got a graph talking about honeybees. I want to know how the rate of population increase changes over time. When is the rate the highest? When would it be concave up, and when is it concave down? So, what's happening to the rate of this change? It's increasing the entire time, but what's happening to the rate of increase? Started out slowly at first, then it got really steep, so it's increasing really quickly. Now what's happening? Starting to level off. It's still increasing, but at a slower rate. Okay, so I'm just going to write the rate was low at the beginning. Became faster. And then slowed back down at the end. Second question, when is this rate the highest? 9 and 15. We could probably even narrow it down a little bit more to maybe even 9 and 12. Would you say that's the steepest part of the graph? Okay, next question. When is our graph concave up, and when is it concave down? Well, it's even starting at 0. You guys agree with that? Until we get to about 12, my graph is curving upward. So concave up from 0 to 12. And then after 12, my graph kind of changes and starts curving downward. So it's concave down from 12 on. So 12 is kind of our magical point here. That's where it changed from curving upward to curving downward. That is actually called an inflection point. So critical points are where your graph changes from increasing to decreasing. Inflection point is where the concavity changes. Alright. So let's see. So we have what's called a second derivative test. The first derivative test was what we were using last night. Second derivative test. We need our second derivative to be continuous. If the first derivative is 0 and the second derivative is positive, then that is a local minimum. If the first derivative is 0 and the second derivative is negative, that is a local maximum. This is at the box at the top of the next page, so you need to fill in local min and local max. Think about what this means. If the first derivative is 0, that means you have a maximum or a minimum, right? Horizontal tangent line. if the second derivative is positive, what does that tell you about how the graph is curved? Concave up. So we have, our options are maximum or minimum for this. It's curving upward, so that means this point is a minimum. If it's curving downward, it would have to look like this, so that makes a maximum. Now the unfortunate thing about the second derivative test is sometimes your critical points and your inflection points are the same. And if the second derivative is 0, we don't know if it's a maximum or minimum. So we still may need to do the first derivative test. Most of the time I use that one anyway, but this gives us another option for finding maximums and minimums. Alright, we're going to try to draw a graph to meet some requirements here. So, first requirement. You have to think about what each of these things mean. The first derivative, f prime of x, is greater than 0. What does that tell us?
That means the original graph is increasing.
Function's increasing from -infinity to 1, and the graph is, or the first derivative is negative from 1 to infinity. If the first derivative is less than 0, that means decreasing. Okay. So until I get to 1, I have to be going up. After I get to 1, I'm going down. We know that much. I'm missing. That's supposed to say f double prime of x is greater than 0. Sorry, I left that part out. So the second derivative is greater than 0 from -infinity to -2 and from 2 to infinity. If second derivative is greater than 0, what is that telling us? Okay. It's less than 0 between -2 and 2, so that's concave down. Alright, third requirement. The limit as x goes to -infinity is equal to -2. What is that? It's like a horizontal asymptote. So, let's see. As you're going forever in the negative direction, your graph's going to get closer to -2. The limit as x goes to infinity is 0. So as you're going in the positive direction, it's getting closer to 0. We have two different horizontal asymptotes here. Alright, let's try to put all this together in some kind of graph. I know until I get to 1, my function has to be rising. Until I get to -2, it is curving upward. So whatever is happening here, we know as asymptotes you get closer to them, right? So we have to be getting closer to my asymptote, curving upward till I get to -2. Between -2 and +2, what's happening to our graph? It's going to be curving downward. Now, does that mean my function has to switch to decreasing? No, I have to still be increasing until we get to 1. So maybe something like that. It's very subtle, but right here my graph kind of switched from curving upward to curving downward. After 1, my graph's going to be decreasing. We've got to get closer to this asymptote, but we are still curving downward until we get to 2. Maybe. And then after 2, it's going to be very subtle, but we're going to switch to curving up. So our graph looks something like this. Questions on that? practice finding concavity for a graph, and then we're gonna pull all the stuff we've done together. So I want to find out where this graph is concave up and concave down. To find that, what do we need? Second derivative. So our first derivative would be 3x squared minus 6x. Second derivative would be 6x minus 6. Inflection points are where the second derivative is 0 or undefined. Is this ever undefined? No, so just find out what makes it 0. So that is at 1. Okay, so 1 is the place where my graph changes from concave up to concave down, or vice versa. We know if the second derivative is positive, we're curved up. If it's negative, we're curved down. So where am I going to plug my test points into? Second derivative, because I need to know if it's positive or negative. So we are plugging them in right here. Smaller than 1 and bigger than 1. If I put in a 0, I get a negative 6. If I put in a 2, I get a positive. So that means my graph is concave down from negative infinity to 1. Concave up from 1 to infinity. Questions there? We're going to do one more example today. And I want everything. I want concavity, inflection points, maximums and minimums, and we're going to draw a graph at the end. So, everything. First, what do we need to do? First derivative. So that would give me 4x cubed minus 12x squared. If I need to find maximums or minimums, I need to find what on this? Critical points. This is never undefined, but it is 0. So if we pull out our greatest common factor, we can take out a 4x squared. That leaves us with x minus 3. So our critical points are 0 and 3. Okay, from this we can get maximum and minimum. We make our number line, pick your test points, and where are you going to plug these in? Okay, so negative 1 squared would be positive. Negative 1 minus 3 is negative, so this part's negative. You put in a 1. 4 times 1 squared, that's positive. 1 minus 3 is negative, so it's still negative. Put in a 4, positive times positive is positive. So we know we are increasing where it's positive, decreasing where it's negative. When you get like 2 negatives in a row, as long as this point doesn't make the original function undefined, you can just say from negative infinity to 3. If the original was like a 1 over x, then you'd have to break it up and say negative infinity to 0 and 0 to 3 for decreasing. Does that make sense? So if you can plug 0 in the original, we can just give one big interval. Decreasing from negative infinity to 3. Increasing from 3 to infinity. Local max and local min. So is 0 anything? What happens at 3? Right, it goes from decreasing to increasing, so that means local min. If you put in a 3, you get out, we put it into the original. You put it into the derivative. Negative 0.7? be 27 times 4, 3 to the 4th is like 27 times 3 minus 27 times 4. So it's 27. Okay. That's the stuff you were doing last night. New stuff. We need inflection points and concavity. So we need the second derivative. Would it be easier to do the factored one or the other? Yeah. So if I do that derivative, we get 12x squared minus 24x. Never going to be undefined, but we can set it equal to 0. We take out a 12x. The inflection points are 0 and 2. Okay, let's check. We're testing for concavity. If I put in a -1, I get a negative times a negative, which is positive. If I put in a 1, I get a positive times a negative, so negative. If I put in 3, positive times positive is positive. So my graph is concave up from -infinity to 0, and from 2 to infinity. Concave down from 0 to 2. Okay, we found lots of stuff. Can I, just for the sake of, since I want to graph, can we get order pairs for these inflection points? If x is 0, if you plug a 0 in the original, we get out 0. If you plug 2 into the original, -16. Alright, let's draw a graph. We know that we had a minimum f of 3 was -27. Let's see. I'm going to count by tens on my y. So 3, -27 is the minimum. I like to mark my inflection points on my graph. I usually use x's so I don't confuse those with my maximums and minimums. So my inflection points were at 0, 0, and 2, -16. We know that our graph starts out decreasing until we get to our minimum. And until I get to 0, it is concave up. So when I just say decreasing, you have two options. You could be decreasing like this, or decreasing like this. Because it's concave up, which of those do I need? The top one. So until I get here, we're decreasing and curving up. Between 0 and 2, we are curving downward. So the change is very subtle. Between 2 and infinity, we are back to curving upward. Now we're going to curve upward, we come down and hit our minimum. And then after 3, our graph was increasing, still curving upward.